Hey everyone, welcome back to yet another Euphoria Academia YouTube video where we do past papers and we show tips and tricks on how to answer the questions. Today we're going to be doing the National Senior Certificate Grade 12 Physical Sciences Paper 1 that was written in November 2023. My name is Ole and I'll be taking you through it. Right, so we're going to be starting off with some multiple choice questions that are related to forces as well as a bit of kinematics. All right, so we're going to start with question 1.1. A constant net force is applied to a block. Which one of the following statements is correct? Well, this is literally the definition of Newton's second law, which is F net is equal to ma. Now, we know that the F net is directly proportional to the acceleration and inversely proportional to the mass, right? So if we have a constant force, then we will have a constant acceleration. This does not change. So our answer is going to be number B. And then for 1.2, we have a crate of mass m on a stationary plane, and it is inclined through an angle theta with the horizontal. Now the question is, which one of the following statements regarding the magnitude of the frictional force acting on the crate is correct? Alright, so the important thing is that the crate is stationary, right, and it is on an inclined angle, or it's at an incline. So we do know that we have our forces acting parallel to the plane like that, as well as that. So that will be the component of gravity. That will be Fg parallel to the plane, and since this thing is not moving, we should have some sort of friction here. So that means we have our Fs like that. Now, if these are not moving, that means that the forces are balanced, right? So that means our F net in this case will be equal to 0, right? So that means if we take down as positive, it means that our Fg parallel minus our Fs is equal to 0. Those are the forces there. So that means our Fg parallel is equal to our frictional force. Now, which one of the options is that? That will be option equal to the component of the weight of the crate, which is Bs. That will be our option A. Question 1.3. We have a ball that is projected vertically upwards from the top edge of the building. Points P, Q, R, and S represent different positions during the motion of the ball as shown in the diagram. Okay, so this is just free fall essentially, because we're meant to ignore air friction. Alright, between which 2 points will the ball undergo the greatest change in kinetic energy? Alright, so essentially when we're looking at kinetic energy, we're just looking at the change of v, which the change of the velocity, where is it the greatest? Well, let's just speak about, so this is the initial point, and then it's gonna go up to a point where the velocity is 0, and then we're going to move some distance where it's going to equal to that vi at some point, but in the different direction, and it's going to go all the way to s, so it's going to have a final velocity. Now you can see that essentially from 0 to s we have a large distance, so that means we're going to have a greater velocity than amongst all these points. Alright, because here we go, it changes and then it's already at 0, right? And then here we're gonna go all the way down from 0 to s, so that should be the greatest change in kinetic energy. Alright, so that will be points. Sorry that my diagram is a bit of a mess, but it will be points Q and S. All right. Number 1.4, we have a ball being dropped from height h and strikes the floor with momentum p. The ball is then dropped from height half h. Ignore the effects of air friction. So with this, we know if we are going to ignore the effects of air friction, essentially we're just going to have our force of gravity, and then we're going to have our potential energy, mgh, being transferred. All of it will be transferred into our kinetic energy. That's exactly what's going to happen. So we're looking at the problem of conservation of energy. Okay, conservation of energy. So what are we told? Which one of the following represents the momentum of the ball when it strikes the floor after being dropped from height half h? So initially, the ball is dropped from a height of h, right? And we're told that the momentum is p, and momentum is equal to mv, right? So through the discussion of the question, I told you that the potential energy is basically transferred into kinetic energy, and that is essentially that will be the momentum change to, so to speak. That's what's changing here. All right. So let us find what our potential energy is equal to. Now, our potential energy is equal to mgh, and like I said, all of it is transferred to kinetic energy, which is mv squared. All right. So in the momentum equation, we have v. So let's write our potential energy in a form of v, right? Which is essentially making v the subject of the formula in this case. Now we're going to see that the square root of gh, or mgh really, but since we all have like a common m this side and a common m that side, we can just cancel them. All right, is equal to v. So let's replace it in our initial condition. Our pi then is equal to our m multiplied to the square root of gh. Now, what is our momentum when h is halved? Now we have h in our formula there. Let's see what we're going to get. We're going to get the square root of g h over 2. All right, and that is going to give us a sum of, if we take out the square root of 2 and just leave this 1 over the square root of 2, because this 2 is at the bottom. That will be multiplied to the square root of gh, and we can actually see that at least this part is the same as that part, right? So our momentum at half of h is going to be equal to 1 over the square root of 2. It's just some algebra and understanding what is happening in this problem, and our answer is going to be B. Alright, question 1.5. A box moves on a horizontal surface. The diagram below shows all the forces acting on the box. Which one of the following combinations do work on the box? Right? Now, work is equal to our force being applied through some cos theta. Right? So essentially, the forces that do work will give us a non-zero answer when we compute our work. right? So in this case, work for Q will be equal to our Q cos, that will give us some angle there, so that is not 0. So Q gives us work, and then for S, we're going to have S cos, now the angle there will be 0, and that cos of 0 is equal to 1, so that will be equal to S, which is a non-zero work, so S will give us work. However, with P and Q, our cos is actually 90 degrees, and cos of 90 is 0. So P and Q give us work of 0. So they don't contribute to work. All right. So the forces that do work is Q and S only. To the main part of the question, which is question 2, and for question 2, it is starting from 2.1 and it goes all the way to 2.4.2, and it's worth 16 marks. So let's get into it. Right, for question 2.1, we're asked to state Newton's second law of motion in words. Now, you should already know your definitions. So for Newton's second law in words, we essentially have F is equal to ma. So you have to say something along the lines that the force is directly proportional to the acceleration, and it is inversely proportional to the mass. So you need to say something like that, but in words. I'm not going to write the full definition, but it's important to go through the definition. All right, for question 2.2, we're asked to draw a labeled free body diagram showing all the forces acting on block A. Now, what is happening in this diagram, right? So we have a force that is pulling two of these blocks, and these blocks are connected by a string that is inextensible, which means it doesn't compress, it doesn't deform, but it essentially transfers force one by one. So if there's an acceleration or movement one way, it will translate it to the other block, and we're at an incline here. That's what's happening. All right, now if we're told to draw the forces on block A, let's just see what we have. Like I said, so we have two blocks A and B, and they're connected by a light inextensible string. All right, so that will imply that we have tension there, and then the blocks are held at rest on a plane which is inclined at an angle, and then a constant force F acting parallel is shown. The blocks now accelerate, so there is relative motion there. And we are also told that, well, above the question 2.2, that we have kinetic frictional forces, right? That means we have friction acting or opposing this motion. Now, if we're going to do a free body diagram on block A, let us quickly do it now that we understand what is happening. So block A is also on the incline, right? We're told that there's frictional force, and frictional force will act parallel to this to the plane that it is on, right? So that means, and the motion is to the right, or up and right, so that means our frictional force Fk will be in that direction, and block A is being pulled by the tension T. All right, and we have a normal force. Normal force will act perpendicularly to the surface that we're on, so it will act more or less in that direction. We have a normal force, and then gravity will always act down, right, vertically down. All right, so that means we're going to have a component of gravity, and yeah, in the parallel direction that will contribute to the difficulty of moving block A upwards. And yeah, just like that, that's our free body diagram. Question 2.3.1 is asking us to find the magnitude of the tension in the string. Now we've already drawn the free body diagram of block A, so I'm just gonna write the information that we already have. So block A is already at 35 degrees now. Let's just compute the forces. Now we know that our F net is equal to our MA. This is not zero because the block is accelerating. We'll take that direction as positive. So that would mean that our T minus our kinetic frictional force minus our component of weight acting parallel, which is W sine theta, is equal to our mass times acceleration. Let us just replace what we have. Our Fk is equal to 5.88. We're given that in the question, minus our what's mg. We have 4 times 9.8, and that is multiplied to sine 35, which is equal to our mass of 4 multiplied to our acceleration of 2. Now doing some algebra, we'll find that our T is actually equal to 36.36 newtons. Right, let's move on to the next question. Question 2.3.2. We're asked to find the magnitude of force F. So I think what will help us is drawing the free body diagram of our block B. Right, so block B is also at this incline, and we have our force F in that direction, and it also has a frictional force attached to it, which is Fk, and we have the component, well, we have weight acting directly vertically down, and we have our normal force acting perpendicularly to the surface, which is that. Alright, now to find F, we essentially need to find the forces acting in this parallel direction. Alright, we're still going to use our F net being equal to our mass times acceleration, where the up and right direction will be taken as positive. So our force F, oops, I forgot something here. I forgot that there's tension as well associated with this. Alright, so our F minus the tension that I almost forgot, minus our frictional force, minus the component of weight acting in the parallel direction, which will be W sine theta, is equal to our mass times acceleration. Let us just replace what we have. Our T, we found that that was 36.36 minus our Fk, which was given as 13.23, minus our weight, which will be our 9 times 9.8, which is multiplied to our sine 35 degrees, and that will be equal to our 9 kilograms multiplied to our acceleration of 2. And when we do the algebra, we will find that our F is equal to 118.18 newtons. And that's the question. Alright, for question 2.4, we're told that that angle there will reduce, right? So what will that do to the frictional force? Well, our answer 2.4.2, and then we'll see the answer for 2.4.1, right? So for 2.4, in any case, we know that the frictional force actually is equal to our mu k multiplied to our normal force, but that will be deemed a constant in this case. So we can see that our Fk is actually directly proportional to our normal force. Now, what is our normal force equal to? Our normal force, if we have a flat surface, our normal force is just equal to our weight, which is equal to our mg. Right, now if we have an inclined surface, like this, we'll just call that theta. We know, and we have an object there sliding apart. Doesn't really matter what it's doing, but we're trying to compute the normal force. The normal force will be perpendicular and the weight will be vertically down, right? Now, for this relationship, in this case, we can see that the normal force is actually equal to the weight multiplied to the cos of that angle there. Yeah, that's essentially it. So if we replace that into our formula, we can see that Fk will actually, let me just, Fk mu k W cos theta, right? If this theta goes down or gets closer to 0, we're going to have our maximum W, and therefore our Fk will increase. If this is kept constant, if the coefficient of kinetic friction is kept constant. Right, now we're told that this thing actually, the angle of the surface actually decreases, which means that for 2.4.1 our frictional force will increase, and this whole thing is essentially 2.4.2, that whole explanation.